Thank you for the nice presentation. So I'm very happy to be with you guys in the middle of the night in Montreal. So I'm very happy to be with you and to share with you some of the challenges that the world of engineering is facing. So I am, as I said, I prepared some general presentation, but knowing what is your area of expertise and so on. And then I have this two section. It's my presentation will be on will have three components. The first component, so I will be presenting somehow IES for you, those of you who does not know the society. And the second component, I will be presenting the challenge of energy production, distribution, and also control. And the second part, it's related to power electronics, new topology that we have worked on the last almost 10 years now on these topologies. So as you know, I am very far away. I am far away from you. I am.
Pardon, sir. Can you make it full screen? It will be better for us.
Yes, I will make it full screen. So I will go and get the other section of the presentation. So I will start with my IES presentation, which is the Society Industrial Electronics Society. So as you know, technology, even though I'm 12,000 kilometers away from you, you are hearing me very well, is it?
Yes, sir.
So Industrial Electronics Society, as you know, it's a community of professional people gathering under the IEEE umbrella. It's a society among 47 societies and council forming the IEEE in order to advance, in our case, industrial electronics, technology and knowledge. Do you guys hear me very well? Is it everything okay?
Yes, yes. Yes.
Okay. So what is IES? It's the professional home of advanced electronics. When you say advanced electronics, it's all the components of electronics, from the microchip, nanochip, from sensors, actuators, the energy supply to all these components, the communication between these components, and after the communication, another level, which is the software, and another level, which is the security of the components. So what is the area that is covered by Industrial Electronics Society? We have the energy conversion and control. We have cybersecurity. We cover robotics and mechatronics. It's one big area, which is the control area as well, and advanced control and intelligent control. We have the renewable energy, everything related to renewable energy. We also have sensors and healthcare application using energy and electronics on the chip. We have the smart grid, digital twin, AI, industrial process as well, Industry 5.0. We also cover electric drives. So it's IES. Our vision is to enable our members careers by building communities worldwide. We are an international society. We want to advance global prosperity to humanity through the creation, the design, and realization of technological innovation, and also through the dissemination of knowledge at all levels. So Industrial Electronics Society is one of the oldest society among IEEE. societies. It has a top rank journals and wide variety of technical topics that are covered, as I saw you. We are about 10,000 members in the society. We are working in many areas, from control system to power electronics, all applied to industrial and manufacturing process and technology. As far as our publications, as you know, probably this is very interesting for you. We have three really very known industrial electronics transactions. We have IEEE transaction on industrial electronics. It's now 70 years of history with an impact factor about 8. 2020, now it's probably a little bit less. We have the Industrial Electronics magazine as well with high impact factor, and we have the transaction on industrial informatics. This is one of the top ranked journal among all IEEE journals. It's ranked number 3 with an impact factor 11.65. It's like publishing in this transaction is like publishing in Nature for people in physics. It's very highly ranked transaction. We also have IEEE transactions on industrial cyber physical systems. Cyber physical systems. It's a new transaction that we just started. It's related to the physical components, the cyber, also the software and the security, and embedded with a physical component. It's the physical and the cyber combined together. We have the GESTIE, Journal of Selected Topics on Industrial Electronics. It's led by our colleague from India, Professor Chandan Chakraborty. It's a very good journal if you have a new subject, you're working on an emerging area, you can use this, you can target this journal for your publication. We also have the Open Journal of the IES. The Open Journal, it means it's a journal that we had to pay, I think $1,800, $1,850 to publish the article, and in this article will be open to everyone to see whether you are IEEE member or a non-IEEE member. We have our conferences, as you can see here. We have ICIT 2024. It will be held next year in Bristol, UK. We have the ISIE, which is Industrial Symposium on Industrial International Symposium on Industrial Electronics 2024. It will be held in Ulsan, Korea. And we have the big annual conference, which is the flagship conference of the society, which is IECON, that will be held in Chicago, Illinois, USA in 2024. We also have other 20 other yearly conferences and workshops all over the world that are sponsored by the society. Among them, your conference also that you are organizing. One important point that we have here, since IES, it's a worldwide transversal society. In addition to the 10,000 people who are members of the society, who are forming the industrial electronics community, our members are also participate in a smaller community. We have sub-communities of interest inside the society. We have, for example, technical committees. We have chapter like your chapters. We have student branch chapter like what you guys are having. It's a community in itself. It's self-organized unit. You take support from IEEE, and you organize events, activities, invite the speakers, DL lecturer, You can invite the society officers also to come and visit you and talk to you about what we are doing. We have young professionals as well, community. When you guys finish your PhD, you are a young professional the first 5 years or the first 10 years probably in your career. So you will have activity dedicated to help young professionals grow in their work and become a mature professional with a big network of communication with the colleagues everywhere in the world. We have Women Industrial Electronics as well, which is a community that is promoting the involvement of women, advancing of diverse talent inside the society. And we have group participating in humanitarian project. We run humanitarian project. If you guys have in your mind as a chapter any humanitarian idea that you want to help people in India, in remote area, or any people, please make a proposal and send it to IES, and we can give you some help, financial help, as to realize the project and make the community happy around you. So please think about something that you think it's useful for your community, whether in the city where you are or in neighboring cities or in villages or whatever. Helping people, helping students, helping kids, helping young kids, boys, girls, and so on. Please come forward and ask us support. We will help you. We have projects up to $20,000-$30,000 from the society. So we are looking forward to have your income for this. It's not moving. Why? Okay. As far as administrative body of the society, as you can see, the society is managed by what we call officers, past president, senior and life member delegate, cluster delegate, and member at large. Those people here forming the administrative committee of the society. What does this administrative committee do? It manages all the activities that you saw in the society. For example, all the conferences, all the journals, magazine, all the publication of the society, all the workshop the society does, and yeah, the conferences as well. All these are, and all the decisions that is taken inside the society, promoting people from student member to senior member to life member to life fellow, also to fellow, life fellow. All these evaluation and accompaniment are done by those people here. The real people, these are the outcome. Inside the outcome, we have like a government. Like this is the government and this is the parliament here, as you are saying. The government is made by the 7 officers, 7 vice presidents. You have the president and the president-elect, and you have the secretary and treasurer. So we have 11 officers forming the government who are managing day by day the problem of the society and the business of the society, the business of the 2,000 people forming the society. We have those 7 vice presidents. For example, Devendra Kumar asked the workshop, the vice president for workshop or for small conferences and workshop to get the sponsorship. So this person gave him get in contact with him, Professor Wee Jung Gao, and gave him all the signed the papers with him on all the contract and authorize you guys to organize in December your conference. IEEE Industrial Electronics Society governing body. This is a photograph of everyone. Devendra, do you see your photograph here? You are here.
Yes, sir. Yes,
Yeah, I think you are here, no?
So, Professor Kamal, that is not Devender, that is Chandan. So, means Devender is the student branch chair. I am the advisor for him. So it is Chandan.
Ah, Chandan, you are here, no, Chandan?
Yes. I visited. I am in that photo. Yes.
Yeah, that's why I'm telling you that you are. Okay.
Yeah. So
Sorry.
that's Chandan. Chandan. Yeah.
Chandan, yes. Now, how to join our communities? Whether you send your paper, publishing your papers to one of those transactions, or to get involved in some industry activities. You have some networking opportunities, and we have support also for students and recent graduates. Also, we have support. We have scholarship. We can give you scholarship. No, not scholarship. We can give you financial support to participate in our conferences, for example. So you have to send your paper and get your paper accepted, let's say for IECON, and ask VP student branch or VP membership to get a financial support to participate in the conference, and you will get the support as well. So it's very good for you. Thank you. This is the presentation of the IES on IES. You have actually, we have the president Mariusz Malinowski, who is the IES president. We have Miloš Maniš, the president-elect, who will be starting his mandate by January 1st, because every 2 years we change president. And the person who prepared all those beautiful slides is Professor Antonio Lucchi, who is acting as a vice president for membership activities. So if you have any questions regarding your chapter, you need support, financial support, or you need to get involved in other activities, please write to Antonio Lucchi. Otherwise, you have access all the time to the presidents as well. We have the email of Antonio, and you have the email of the society website, and you have access to all the material that the society has. Do you have any question regarding IES before starting the other presentation? So I'm concluding on this, on the society. Do you guys have any questions? Or any comment would you like to ask or whatever? I'm ready to answer. Hearing none, so I will go ahead with. Okay.
Yes, sir, go ahead.
Hearing none, so I will go ahead and continue the discussion with you. So the challenge for producing energy till now, we have the polluting sources of energy, and we have the classical clean sources of energy that we are producing nowadays for our societies. As you know, you can see here the hydropower. You can see here the wind and solar panels and all the ongoing energy, kinetic energy that is converted into electrical energy. So this energy produced mainly is distributed using some people call it ugly transmission lines, because some people, they don't like the shape of these pylons, but we need the transmission lines because the center of production is not nearby the center of consumption. So therefore, we need a distribution, transmission and distribution network in order to supply through substations, several substations, the cities that are energy poor, consuming the energy. After the distribution system, so we generate energy here using hydro generator at 30 kV. From 30 kV, we put a boost transformer to boost the voltage from 30 kV. Like in Canada here, we are using 735 kV on the transmission line. And when we transmit the energy, when we are close to the city, we reduce the voltage level to whether 120 kV or 69 kilovolt. And then we do the distribution for residential area on 25 kV to 120 volt or 240 volt. And the energy is used for energy storage, EV charging, distributed energy resources, and so on. And also we have the commercial, industrial loads. So nowadays we are working on making this system more intelligent system. Intelligent system mean I cannot make the pylon intelligent. I cannot make the alternator intelligent. I cannot make the wire distribution wire intelligent or a transformer intelligent. What do I make intelligent in these? I have to add a components to the actual system, and I have to interact with the components, so then I can read in real time and I can act in real time, as well as I can take a decision, as well as those components can take a decision. So those components, they will have a minimum of artificial intelligence or machine learning algorithm. So as for several data, they can take autonomous decision and so on. And this is a new area of research, the surveillance and the control on these distribution, production and distribution system. Now I'm giving you here a couple of examples of battery energy storage system that has been installed around. They are around now. It's a reality where you have, this the example is we have 2.4 megawatt hour lithium phosphor type of batteries, as you can see here, in order to support a remote network supplied by the utility company. We have 1.2 MVA DC to AC power converter here. This is a grid connect converter, but it also can operate in standalone mode. We have the converter here is powering a pump boost transformer, which is boosting the voltage from 480 volt three-phase delta connection to a Y connection, 25 kV, which is connected to this substation that you can see here through an LCL filter that is found here. This is another example nowadays. Also, you can see the battery energy storage systems moving around when you have a fault on the utility side. Instead of bringing big diesel generator to supply the neighborhood, now we are bringing a less noisy, less polluted type of battery energy storage system, which is based on lithium-ion battery type of battery that we are using. But I'm losing the control. Okay. Distributed energy resources. So look at here. We are not very clean everywhere. So I'm giving you here a figure where you can see, guys. This is Canada with the white. Where is my pen? This is Canada here. It's the upper side of North America. This is the Canadian territory. From Quebec is here, where I am. Quebec is here. From Newfoundland till British Columbia. So it's a very big country. You can see here from where our energy comes. On the east side, as you see here, you have this blue dots. These blue dots are the hydroelectric generators. So we have very many hydroelectric generators here. We have here on Ontario, we have much less powerful generators. This part of the country, the west part of the country, we have on BC. We have a lot of hydro generator as well. But Alberta, you can see everything is red or black here, black also, and small green, very small green cell. So it means that in the both section of Canada, we are using, because we have hydropower resources, and the others are using the classical natural gas, coal, nuclear. The yellows are nuclear, what you can see here, nuclear plants in this section. The coal are the black dots that you can see. So it's not, we don't have, not everything is renewable energy. As far as USA, here what you can see, very rare to see hydro, very few hydro dots, as you can see here on the east side, some, and on the west side as well, because here where you have the water, a lot of water here in these states, and everything else is whether it is natural gas, the white dot, or the nuclear, or those red dots that you can see here. Coal is the major energy production in USA, as you can see. These are the black dots tells you that all these are the production made by polluted sources. Wind, you can hardly see wind. Nowadays, it's growing very fast, but still, it's not the bigger energy production. In Canada here, what I gave you, I want you to know, I won't go into the detail, that we are going forward. We are moving slowly. We're not moving at very high speed toward reducing the fossil, the gas, the nuclear. We almost shut down most of the nuclear plants. We are reducing also the gas, and we are moving. We want to be less gas and zero nuclear, and moving toward renewable energy. So we have been increasing the contribution of. We are planning to increase the contribution of Canada's solar and wind energy by 5.2 gigawatt coming from solar, and we are scheduling also to increase. We have increased by 1.8 gigawatt in 2020 as well. As Canada added 9 gigawatt of capacity in 2020, which is more than 75% is coming from wind energy, and we are going, I will show you the statistic. We are going forward to increase, as you can see here. We are planning to reach by 2050 zero net greenhouse gas emission. So it means that all our energy production that we have will be mainly 178 gigawatt, mainly from renewable energies. So this is what is planned. Now we are here. We want to go up to here, and this is the planned one. Actually, we are here, and we are moving toward this kind of planning for the next 30 years almost. Like everywhere, India also the same case. We need to multiply by 10 fold the expansion of our wind and solar energy capacity. And here comes the business, because you guys, you are in the business of energy, and you want to develop technology and sell it to the world. Very high efficient technology in the area of whether it is solar, or it is a wind, or whether it is a technology related to the transportation and the electrification. So you are in the best timing to do business in this regards here, because everybody is planning. Most of the countries on the northern part of the hemisphere, and I'm sure the southern part of the hemisphere, are doing the same thing, that they want to have at least by 2050, 2/3 of the energy production comes from renewable sources, as you can see here. As for Canada, we need to deploy 3.8 gigawatt of wind energy and 1.6 gigawatt of energy annually for the next 27 years in order for us to meet the target that we are planning to have here. So it's a big effort, and this effort doesn't come from nothing. So if we wanted to meet the by 250 net zero energy, we have to reduce our emission drastically, as you can see here, from 739 megaton of CO2 per year to zero. Very simple. And this target has been set by the politicians, and we need to respect. Now, toward more integration of photovoltaic, electric car, energy storage devices in the future power grid. Look at, I'm giving you here an example of what we have. This is the beautiful example of a country or a province like where we have 90, I would say 95% of our energy from this province here comes from hydropower. You can see here all the dams are here. In the east, we have two V type of electric network. This is the best example of unstable network, where the production are here, thousands of kilometers from the consumption and the clients and here. So we have to produce, transmit, and distribute the energy into all these areas. So we have 35,000 kilometers of line, different voltages from 735 kV till 12.5 kV or 480 kV on the line. Depends on how far or how close we are to the clients. As well as, this is another issue that you guys can work on. We have about 2.7, we have 10%, more than 10% losses, the electric energy losses declared by the utility company, where 7.5% on the network of transmission and 2.7% on the distribution losses. So we have more than 10% losses into all these equipments, and though we have a very young and almost an updated transmission line. So if we are talking here about a power, our capacity here 37 gigawatt of power. So if we are losing 10%, that's a lot of power. That's 3 gigawatt of power lost on the line. So we need to design a high efficient smart grid system in order to save all these energy and use it in a proper way for the people here. We have utility company, they don't own all the time all the energy that they are selling. Like the best example here, the utility company Hydro-Quebec, the utility company own 37.2 gigawatt of installed capacity, but they have access to another 10 gigawatt through private producers through a contract. So the total capacity of the utility company is 47 gigawatt. Among them, 37 they decide on real time what to do with the power, and the other 10 gigawatt they have to import and export to other private supplier that are found in the country. Electricity production in 2020. Now the government is. I will show you the plan. 94% of our energy comes from hydroelectricity, and 5.2% from wind power, 1% from biomass, solar, and diesel. We are not a country who is rich in solar energy either. Globally, our forecast is in match with the global world forecast. Global world forecast, as you see here. So our consumption in fossil is reaching the top, and with all the effort that we are making nowadays by producing energy through renewable systems, we are controlling the peak. We're not going up at the same slope. Look at here. We are going at the same slope. Here it peaked up. And since 2010 and around 2010, we started the wind turbine and the renewable energy effort. So we reduced the slope from 60 degrees slope to almost 45. Now we are reaching almost a zero slope, and we are hoping to go down in the next years, the next 50 years, the next 30 years, in order to control the pollution and the greenhouse emission by those units. Same thing, renewable energy are projected to make up the bulk of the power by 2050. If you look at here, these two zones, this zone here, which is the solar is taking extremely high importance as the wind onshore and the wind offshore, the combined wind onshore and offshore will equal to the solar. So these parts here on the production side will account for more than 50%. This is a realistic figure here. So we are targeting 2/3 here and 1/3 this part here. So if you account hydro, wind, on and offshores, and also solar and other renewables, we will have more than 2/3 of the energy produced by clean power. This is what we want, and this is the target that everybody is. And this target is, as you can see here, you can feel it by the investment. We are putting a lot of money. Look at the amount of money we are putting here. Investment in $1 billion, for the next 30 years. Most of the money here are going to power renewable. Look at the power renewable is taking the whole part, big part of the investment that we'll be doing. And the power transmission and distribution line, all the distribution and transmission line that you have seen till now will be completely changed as to adapt to the new reality. So we'll have a new set or new type of transmission and distribution line. In order to confirm all those prognostic that is made by a society that do conduct the studies, I'm giving you the real example of where I am here, that the utility company, our utility company, they have been spending $4 billion to $5 billion annually on investment and operation expenses for the past 20 years in order to maintain a almost 40 gigawatt power system operating with zero error, with zero interruption, almost zero interruption. You can never lose electricity here unless in extremely rare cases. Now, the tendency, Hydro-Quebec is now tripling the investment to the range of $12 to $16 billion a year in the equipment of the smart grid, what we call nowadays the smart grids, which is twice as much as what we used to spend during the 70s and the 80s when we started all these networks. And look at this, the prognostic, and I saw the last week the presentation of the big chief officer of the utility company. They are planning to invest $90 billion to $100 billion in order to make the infrastructure updated and available for the future to produce renewable energy for transportation and electrification. So most of the investment, the future investment, will be going into the energy sector. So you guys, you are in the right place at the right time. So it happened very rarely, but we are really enjoying being specialists, energy specialists, during the right time. Now, where does all this energy goes? why we are producing those energy and where the energy goes. Look at our cities. If you look at those cities, each one of these towers, let's say in whether you are in Toronto or in Vancouver or in New York, all the cities are made of big towers, and each of these towers, guess how many megawatt power? Minimum 2 to 3 to 4 megawatt of power needed to operate each of these towers. The capacity, the installation of the nominal capacity of the installation for each of these towers, it's about 4 megawatt. So this is where the energy goes. What people are doing into these towers, they are working, they're using computers, they are using printers, they're using communication system. Nowadays, they're using the communication system is the fastest growing energy-vor system in all those buildings, because you have to store energy, you have to store data. Data storage also is taking a lot of effort, big part of the energy. As well as you hear very many people are now talking about moving toward the smarter cities. Smarter cities means what? Means more electrons, more megawatt, more gigawatt be needed to make everything smart. But because everything smart means sensors, smart means bidirectional communication, bidirectional data, many data to be treated, and each of these data that I'm talking about necessitate a lot of kilowatt hour to transfer that. I don't know how many kilowatt hour I will be using tonight, for you this morning, to make you see all my slides and communicate with you, and you are seeing me like I'm sitting by you. I have no idea, but I can tell you one thing, that probably in the future, when I start this kind of the same presentation, like 20 years from now, I will have here on the screen a counter telling me how many kilowatt hour I'm using, and I will pay per kilowatt hour the energy I'm using. And this energy, this payment, this dollars can go to whether to India utility or Canadian utility and whatever. So everything will be accounted and paid. Now you hear more and more about smart cities, about electrification. This is an example of a train that I have done. The power supply of this train I have done in my research lab for Jacksonville Utility. You will see all these kind of light train everywhere, driverless, moving people from one place to another, and everything based on electricity. So the transportation electrification sector is booming, is growing very fast. It's not only a train, but you have many other type of micro mobility, single person mobility, or two persons mobility, or three people mover, or a train, or light train, or a small train. So it's a billions of dollar business, and everybody, or bike also, biking, electric bike has also become very popular as well. Moving ahead at a higher level, we have the fleet electrification waves. Everyone for transportation, for trains, for buses are moving ahead with electrification. So it means that a lot of energy. Look at the forecast for electric vehicles by 2030, by 2050. Everyone is expecting exponential growth for grid connect multiple devices who are taking the energy from the grid and putting it into energy storage devices. Till the moment we are talking about lithium ion batteries, but we are moving ahead toward solid state type of batteries. So all these electric vehicles need energy, need kilowatt hour. We have to put kilowatt hour in all those batteries. So from where will come those kilowatt hours, and what's in those electric cars as a structure, and do we have an optimal structure? Till now we don't have any optimal structure. As you can see here, if I am the utility here, I'm supplying this traction chain. What do I have? I have to protect the utility. In order to have a good power quality, I have to use some filters, AC filters. I have the charging station here. Charging station can be level 1, level 2, level 3, or a high power. Nowadays, no one wants to use level 1 and neither level 2. Everyone wants to go with a minimum of power of 6 kilowatts and up to 10 kilowatts minimum. So everybody wants to charge, and every car, electric car battery kilowatt hours is going up. We used to have 20. The first Nissan car was 16 kilowatt hour. Now the least Nissan car has 40 kilowatt hour energy devices, energy storage battery. So if you are supplying, if your battery charger is 10 kilowatt, you need minimum 4 hours to charge the car, and so on. So we keep on increasing. We have the battery, we have the traction system here, we have the auxiliary system to supply. So look at this. This is for every single car. We have this scheme. We have this converter here, and we have these converters inside the car. So we have 1, 2, 3, 4 power electronics converter. We have the filters. We have the filters to add on both sides here in order to make a system acceptable. So we have so many power electronics components. Now we are talking. We used to talk inside the car about having a battery pack of 350 volt. Now we are going ahead for 500 volt, and we are seeking up to 800 volt because we want to increase the transportation range. So the voltage keeps on increasing. The kilowatt hour also, it keeps on increasing. Now we have the latest Tesla model. We have 100 kilowatt hour battery inside. So one can imagine that in every building, in every building of this tower that you saw, this kind of scheme that we have to supply. So if you are the person who is making the electrical battery chargers and you are putting your filters, your filter will be everywhere. Here we will have filters. Here we will have filters. We will have also here some compensation, some filtering effort. So we'll be having reactive components everywhere, and those reactive components, if you with the utility impedance, the reactive impedance, inductive, capacitive, we will be looking for a big problem, which is the trouble of having a resonance phenomena, and those resonance phenomena ended up, as you can see here, because of the harmonics that are circulating between the components that are not controlled, ended up with burning all the distribution transformer, because those transformers are not designed and rated to supply all these energy all the time. So unless we have to change all the distribution transformer as well, so which is extremely costly things to do. What are the bottlenecks that we have for in front of us? The road is not, though we are spending a lot of money, but the road is not clear all the time. We have a potential bottleneck that include, if we are talking about wind turbine, we are talking about solar energy, we need land availability. We need a new infrastructure, energy infrastructure. We need manufacturing capacity for this big changes in our way of producing and distributing energy and making smart grids, bidirectional grid. Consumer affordability, do we have a consumer investment willingness also, and as well as the material availability for all those power devices that we are using, where the electrons are flowing through. Another possibility, the green hydrogen faces high risk mainly due to infrastructure needed. So we're not hoping that with the hydrogen will be as energy storage system can flourish very fast and rapidly, and it requires a lot of investment also and a lot of safety associated with. Rare material also, it's a big challenge as well, because all these magnetic material that we are using, whether for the wind turbines, wind generators, the EVs, and so on, the batteries material, all these rare materials, it's a big challenge for humanity. And the cost also, the price is very expensive still. But nowadays, the latest study showed that EVs and heat pumps are expected to become really economically viable technology. So this is a very good news. So all technology related to electric car, EVs, and also to heat pumps. Heat pumps, it has power electronics nowadays in it. And heat pumps power can go from several hundred of watt till several kilowatts, also for big space and big buildings, several tens of kilowatts. So it's a big area that we don't know very much about it normally in power electronics. Not everyone work on it. So this gives you a good idea about the wind energy and the challenge that we are facing. If you look at what I'm highlighting you here, one research area which is very important to all. This research area is about, look at the example of wind turbine. And this is a case study that is found here. Look at this wind turbine. You have the rectifier here. We have the annular generator, the rectifier. We have the DC link. You have the inverter. You have here the passive component, which are made of the filter. After the inverter, the filter, the transformer that pump up the voltage up to 120 kV, or we are having inverter here at 480 volt. So we are pushing the voltage here to 31 kV and connected to the grid through a collectors, AC collectors. So we have to have a filter here, as you can see. So if you look at this case here where we have 44 wind turbine, and this is a real case study that I work on. We have 44 wind turbine, each one totaling 100 megawatt of capacity, distributed within 3 sections. We have to find the land, the appropriate land, and install all these equipments. So we have 1, 2, 3, 4 section in the land where they are neighboring, and we have to collect the power. 44 wind turbines, each one of them is about 2.3 megawatt. So we have 100 megawatt total active power with a very small capacity in megabar here, because the rules and the regulation doesn't permit very many megabar, so it's limited megabar capability here. We cannot take all the megawatt and try to compensate the line. So what this is the first section. We call it CE1, CE2, CE3, and all these are connected to the booster station, here, which is connected to the utility. Now, what's the problem with all these wind turbine? The filter. Why the filter is a problem? Because the filter, these are reactive components that are distributed all the way here and interconnected together. So what this filtering problem is bringing, imagine this network here with all those impedance to which we are adding those filters. If I remove the wind turbine, I replace them by the filter, which is the case, I will end up having this network. Now this is a network, depends if this is this a stable network? The answer is no. Why? Because if I introduce any harmonics close to any resonant frequency of these branches, I will excite the circuit, and I will end up having resonance, and I will have thousands of amps circulating between the components, and I end up which is most of the case, blowing up the converter and the filter that is used in those wind turbine. So what is the problem to that? We need to have a solution where there is no filter whatsoever. We need to remove those filters, and in order to bring back all these to first order type of load instead of having them X order type of load. Another big problem that we have that I want you to be aware of, this will lead you to design much more efficient power electronic system, which is the drive. The low voltage motors, 28% of the energy produced are consumed by those low voltage motors. You have the low voltage motors, you have the medium voltage motors, and look at here. Medium voltage drives. This is the low voltage drive. 150 million unit a year of low voltage drive. Very cheap. Medium voltage, some of the medium voltage at lower power, 12,000 unit. Average price $240,000. Medium voltage motor, 60,000 units a year, 100K average price. So low voltage motors are very cheap, $300. What's the problem with these? The problem that those who sells the motor doesn't sell the filter. This is an example that you can see here. ABB, Baldor, Siemens. So Siemens is the first seller of these low voltage market share drives, and these are the motors. Siemens also one of the first motor producers in the market. So how these are affecting the whole drive? If you are buying the motors, you're not buying the drive. You have to buy the drive. If you are buying the drive, you need to add a filter on the AC side, and you need to add another filter at the output of the converter. And if you have a long cable to supply to the drive. Okay, so what's the problem? Look at here, 25 HP drive costs about $2,500. Output filter, $2,500. Input passive filter, $3,000. So you are multiplying, you're not designing only the drive, but you have to take care of both filters. So you can sell the drive, or you say my drive is $2,500, but it doesn't work alone. You have to add all these, so you end up multiplying by 3 the price of the system. What's the solution? Can I remove this? No, I need to control the energy. So this is the only element where I can control the energy between the 3-phase AC and the motor. Can I remove this filter? Yes, most probably. If you generate less EMI and less dV over dt, you don't excite your cables. You're moving signals, propagating will be less higher, and you don't double or multiply by 4 the voltage across the motor here. So you can eliminate or reduce drastically this filter. How about this filter, input filter? Yes, definitely we can remove this filter. How can I remove this filter? I need to have a converter that does not generate any harmonics, very low harmonics level, current harmonics or voltage harmonic here. So as I do not need this bulky filter here. So this is the necessity of having filterless type of systems. Look at the nominal voltage that we are using here, 3-phase 6-switch bridge. It's the most cheapest one, but with this converter, you will end up having spikes on the motor side. Even if your VDC is 500 volt, you can end up having spikes up to 3 kV peak to peak. as you can see here. It's using a 6-switch device is not a solution. Now we have to go for much higher probably level of converter. And then what is the LC filter bring into the converter? Look at the LC filter model, because the switches here are so fast. So what is the equivalent circuit of the converter? It's the output filter that we are having, the output passive filter and the load. So if we model the passive filter and we model the load, we end up having this transfer function here. Now this transfer function may be stable, may be unstable. So we want to work on the stable side of the diagram, the plan, the frequency plan. So we have a very complex transfer function, and we need to design exact value of L and C in order to stay stable all the time. So this passive filter create problem interaction between the LCL filter, which is connected to one or several buses, which is the case of wind energy, where we have 44 type of these LCL filters spread over probably 3,000 square kilometers of land. This will limit, the filter will limit the bandwidth, and also this filter is sensitive to load changes, depends on the impedance of the load that you are connected on, which is prone to resonance risk that can be found with this. Then what is the ultimate goal? The ultimate goal is not to have any filter. Just connect, make the converter behave as a first order system, not generating any harmonics, so you don't need your filter, and you go ahead and reduce the filter size to a minimum. At the limit, people are dreaming, and I am one of those people who are dreaming of having using the network impedance as the filter without adding, and in worst case scenario, adding EMI filters to the converter and not big bulky filter. So converter with reduced rated output passive filter, the advantage of these, we can eliminate the heavy, bulky, and costly output filter. We will have wide bandwidth of the inverter instead of having inverter with 1 kilohertz bandwidth. We can go up if we don't have the filter. If we have zero filtering, our bandwidth will be the switching frequency of the converter. So that's a big margin here. We will have high power density converters. We will have faster dynamic response, definitely, and output filter resonance will be eliminated because those filters will be reduced to a minimum. Then what will be the disadvantage of this approach? The disadvantage of this approach that we may need numerous components of in order to ensure that we have a higher number of voltage levels. In order to ensure that, we may need a lot of components, semiconductor devices. Okay, if we are talking about so many components, then we need a digital controller with high-speed interface in order to control all these number of components. And as well as converter control will become more complex because controlling 6 switch is not like controlling 240 switches feeding the same drive. Then we're not talking about the same scale. And I will give you the example about how we can go from 6 switch to 204 switch MMC type of converter for AC drive. Now, if we want to have a beautiful and no filter, then what's the answer? Look at here. If you look at here, the number of output voltage level that the converter can supply, and on the x-axis, the THD, the output voltage of the THD. If we want to have a less than 4% THD less than 4% THD at the output voltage, we need 31 voltage level. So if I'm having DC bus of 500 volt, I need to split this 500 volt into 31 voltage level in order to have an AC, a beautiful AC signal, which is 4%, less than 4% this harmonic distortion. It looks like exactly the same quality of signal as given by the utility company. I can do even much better than that. I can go up to 85%, 85 voltage level. It will give me 1.42. And this signal is not found with any utility company. None of the utility company of the world is delivering such a beautiful quality of signal with 85 level. The question is, can we have this 85 level? Yes, we can. At what price? We can discuss it. Definitely, we can discuss it. Can we have 29 level and accept 4.3% THD? Yes, it's very reasonable to have 29 level line-to-line voltage, 29 level, and get it. So it's reasonable then. When you see here the orange color here, where you have high THD, and the green one section. So if you want to replace and not have a filter, you have to have a converter with at least 29, I would say 29 level output voltage. Who can give you this 29 level output voltage? Look at, for example, here, the 9 level inverter per phase, which is 2 times 9 minus 1, 17 level line to line voltage, can give you a phase voltage of 14% harmonic. So it's not enough, 14%. This is without filtering. I'm not talking about filter because I'm targeting here and I'm trying to encourage you to have no filter as I show the problem of the filter. If I move up to 13 level here, inverter, 13 level L times 2 minus 1, I will end up having line to line voltage 25 level. 25 level, this will give me 9.6. I'm still high in harmonic. If I go up to 41 level line to line voltage, which is 21 level inverter per phase, I will end up having 6.31 probably. So 29 level will give me 4.31. This is completely filterless inverter. So I will be happy not to use any filter. And I am reducing the size of the components drastically, and I am reducing also the use of filters and the reducing the cost because of those filters, and I'm increasing the bandwidth of the converter because I don't have a filter, bulky filter, so my bandwidth, I can have higher dynamics, I can apply advanced control, very fast control, and control all the parameters. So here is the question. If I do this, look at here, all those wind turbines that have the filters will be removed. I won't need those filters. Look at the number of filters that I am using here. So I won't use them. If I won't use this filter, so I will have a very stable network with transformers and cables. This is 100% stable network, and I will never lose the control of the wind turbine. And you cannot imagine the number of faults those wind turbine that they are going through. I'm promoting here the multi-level type, the use of multi-level type of converters, which is to answer the request. Why multi-level type of converter? Because those converters are having reduced dB over dt. We are switching, instead of swinging 500 between 0 and 500 volt, I'm splitting the 500 volt into 10, let's say 10 section, and each section will be 50 volt. So my dB over dt is reduced by 10. If this is the case, I'm subject to less EMI, less dB over dt, and also less dE over dt in the cables because of the reduced dB over dt. If this is the case, I can go ahead and reduce the switching frequency. And by reducing the switching frequency of the devices, consequently, I'm reducing the power losses. I will have higher efficiency, less electromagnetic interference, and I will have a fault tolerant also capability as well. So this is very good. Then why don't we use all these converters nowadays? My message to you here that we need to use these type of converters, because these are the converters who permit us to, whether we are at 2 levels, as you can see here, whether we have 2 levels, we can go up from 2 level to 3 level. From 3 level, we can go up and up at much higher levels, as you can see here. In this is an MMC H-bridge type of topology, where you can have 9 level on each of the switches. Here we have 1, 2, 3, 4, 5. We can have 7 levels times 2, 14 minus 1, 13 levels line to line between 2 legs and so on. So we can stack more H bridges and have much more levels as well. So this is the idea. What's the drawback of this type of topology that we are having? What's the drawback of having these? Excessive increase of the number of components. Yes, sure. At higher number of voltage to obtain the higher number of voltage level, but here we are having components with much less voltage stress on them. We need advanced hardware. Yes, we need very highly advanced hardware to accommodate and control these high number of components, and therefore we need higher signal processing capability, and we definitely need to use, and this is the tendency nowadays, we are using FPGA to control all these power electronics devices. Will this lead to more complex control and modulation method? Yes, but it's not impossible nowadays. With the tools that we have, we can have this this luxury. I'm losing the control. This luxury type of converters. What do we have in topology among all those multi-level converter concept? Look at here, with the main MLI topologies are modular, PWM topologies are the neutral point clamp, the cascaded H-bridge. We have the flying capacitor multi-cell. We have also the active neural point clamp, the ANPC, which is the most popular one among all those topologies. And we have the MMC topology as well. The MMC, the advantage of the MMC is that we can go ahead and get connected to 25 kV or 47 kV line systems, you know. So this will be a very good topology. I am sorry, it's already 12:30. It's been 1 hour and a half. I mean, the time went so fast, and I'm still have so many materials. I would like to open the discussion. I don't want to take all your time, guys. We can have another meeting some other times, because I have other materials that I didn't show you, because we have gone. I wanted to show you some of the. Where is it? I'm losing control on my computer. I don't know why. I want to show you some of the topology that I can show you. Probably because I have a big file. I'm losing control. My team we have introduced here, probably. We have introduced some of the topology that gives higher advantage. We have created nowadays 12 new topologies that permit to create an impressive number of output voltage levels. We are calling it PAC, the BPAC, the PAC, the BPAC, the HPAC, the BHPAC also. And we have the generalized ZPAC type of topology. We have the ZPAC MMC topology. And I have introduced also the modular voltage level multiplication. So if you enter a signal here at low frequency, we have a converter that multiply the number of voltage level. We can have six-fold. So if I have here 3 level or 5 level, I can have 31 level out the output. If I put 2 cascaded 6-fold, I can have 36 times 5, 185 volt at the output as well. So I have introduced the voltage level multiplication type of converter. This is an example of new topology that we have introduced lately as to reduce the efforts, the filtering efforts, reduce the copper, reduce the overuse of copper. You know, those coppers are extracted and we pollute a lot of, we change the nature by extracting all these from the earth, and we are using a lot of iron also for these converters as well, and a lot of material. So material, if we use less material, is the best for the environment and the more efficient work we can do. Also with the probably the new technology, the wide band gap now with the fast switching and high performance, we are hoping to reduce very much the losses, the switching losses and the conduction losses. Because with those topology, we're not switching at high frequency, we are switching at very low frequency. So we don't worry very much about losses due to frequency, though we worry because, for example, these topologies, the first 2 switches operate at the fundamental frequency, but the last switches who has the least voltage operate at higher frequency. So we end up using a low voltage, high frequency device, but still we're not operating at 100 kilohertz or 200 kilohertz. We're operating here at like 10 kilohertz and less, and we are having beautiful sine wave, output voltage sine wave, very much controlled. So I would like to stop on this because I don't want to abuse your time. It's 12:41, so we've been 1 hour 40 minutes discussing. Probably next time I will go visit you guys. I don't know. I have no idea. Or you can, I can visit your conference next year and discuss all these new topologies and the challenges. Thank you very much for having me, and I am open to any of your questions if you have any. Otherwise, I'll let you go and continue your